This lesson will be about binomial experiments. A binomial experiment is a special type of experiment with the following properties. The experiment has to consist of n repeated trials, where n is a fixed number. Each trial only has two outcomes, one of which we usually denote as a success and the other one is a failure. The probability of success is the same each time. And all of the trials must be independent. So an example of a Bernoulli experiment would be flipping a coin 10 times. So n is our fixed number of repeated trials. A coin only has two outcomes, heads or tails. The probability of getting heads or tails each time is the same, and whether you get heads on one trial does not affect what you get on the next, so the trials are independent. What about drawing marbles out of a bag that has green and red marbles until I get a red marble, and not replacing the marbles? This is not a binomial experiment for two reasons. One, there is no fixed number of trials, because I'm just going to keep repeating trials until I get what I want. And also, the trials are not independent because I'm not replacing the marbles as I go. Now, let's look at how to deal with probabilities involving binomial experiments. I'll explain this using an example, and then I'll write a formula to generalize. So let's say I'm going to be flipping a coin 4 times. Let's examine the probabilities that I get 0 heads, 1 head, 2 heads, etc. So the probability that I get 0 heads means that I would get tails on every single flip. So that's 1/2 for the first coin flip, 1/2, 1/2 times 1/2 4 times, because each time the probability that I land on tails is 1/2, and all our trials are independent. This gives me probability of 1/16. Now the probability that I get 1 head is a bit more tricky, because I can get 1 head in several ways. I could flip heads, tails, 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 head, tails, 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 head, then tails, or I could get 3 tails in a row followed by 1 head. The probability of each of these individually is 1/16 by the same reasoning as we calculated this first one. And so the probability in total that I get 1 head is the sum of all of these, which is 4/16, or 1/4. Notice that the ways in which I can get 1 head is essentially equal to having 4 spots and choosing which one I want to get the heads in. So, for example, this one corresponds to choosing our first section to put in heads. The second one corresponds to choosing the second spot to put in heads, etc. Now let's look at the probability of getting 2 heads. This is even more complicated because there are even more ways we can do this. We can get heads, heads, tails, tails, heads, tails, heads, tails, head, tail, tail, head, tail, tail, head, head, tail, head, tail, head, and tail, head, head, tail. And this is effectively the same thing as having 4 spots and choosing 2 of them in which to put in heads, or for combination 2. Again, the probability of each of these was 1 out of 16. So I'll multiply that by the number of combinations I had, and I end up with 6 out of 16, or 3 out of 8. By now you should be seeing a pattern. Essentially what we've been doing for all of these is taking the combination of 4 by the number of successes that we want and multiplying it by 1 over 16. So for our first one, where we wanted 0 heads, we would take combination 4, 0 and multiply it by 1/16 to get the probability of 0 heads. So you can guess that if we want the probability that we get 3 heads, then what we can do is take combination 4, 3 and multiply that by 1 over 16. Now let's consider what would happen if our coin was weighted. So what if the probability of getting heads on any trial was equal to 1/3, while the probability of getting tails then is equal to 2/3? Then what would happen? So let's examine the case where you want to find the probability that we end up with exactly 1 head. Again, this still can happen in combination 4 choose 1 ways, because we still have 4 spots and we're choosing one of them to fill in with heads. But we're going to be multiplying by a number other than 1 over 16. To see why, let's take an example of a sequence that has 1 heads. So let's say this is tails, head, tails, tails. Probability of getting a tails here was 2/3 times the head, 1/3, 2/3, 2/3. Okay, so what we have here is 1/3 times 2/3 to the power of 3, or the probability that I get heads to the power of the number of successes that I wanted, times the probability that I get tails, or not head, to the power of the number of failures. So that's what I'm going to put in here. Probability of head to the power of 1 times probability of tails to the power of 3. At this point, we should be able to have an intuitive understanding of the formula for a binomial experiment. So say you have a binomial experiment that you're going to perform n trials with. And each trial has a probability p of success, which means it has a probability 1 minus p of failure. And you want to know the probability that you get k successes. The formula for this is you'll take the combination of n, choose k, multiply that by the probability of success to the power of the number of successes you wanted, times the probability of failure to the power of the number of failures that you wanted, which is equal to n minus k.